Section 8.5 is titled Partial Fractions. One or two of you have said you think you might have heard of this before. The basic idea of partial fractions is not a calculus technique. It's something that is completely and totally algebra. And there's a note on your paper that says this. There's a note, once I flip to the next slide, that's going to say that as well. However, it's one of those topics that's often skipped in college algebra because there's so much to cover anyway, and unless you actually get to Calc 2, it's not really necessary for anything else. And now you guys are here and you're in Calc 2 with me, and now it's necessary for something else. In particular, it's necessary for integration techniques. So the basic idea of partial fractions is taking a fraction that has factorable denominator and factoring it and trying to separate it into two separate fractions that are added together. Okay? So we try to get common denominators all the time and we mush fractions back together. We do that all the time. Well, what we're going to be doing in this section is pulling them back apart. And if we can pull the fractions back apart, that often allows us to do the integration, whereas we couldn't have done it before. Okay? So the idea is to do a decomposition of n of x divided by d of x, numerator divided by denominator. So the first thing you're going to do is you're going to divide if in fact the degree on top is larger. So like long division. That's what that is. Okay? The second step, the first step doesn't happen real frequently. So let me just kind of make that note to you. It doesn't happen real frequently. So most of the time you'll find yourself starting at the second step, which is to factor the denominator into its parts. The third step is to write the denominator as a summation of fractions. I don't know why my line did not get all the way underneath fractions, but it should say summation of fractions with each factor of the denominator as a separate denominator. So in other words, if the denominator can be factored into x times x plus 2, you're going to have one fraction with a denominator x, another fraction with a denominator x plus 2. You write the numerator of each of those fractions with a degree 1 less than the denominator. And I will tell you that everything up to step 4 is very quick, especially steps 2, 3, and 4. They're very quick steps. The reconcile on step 5 is the hard part. Reconcile the created summation with the original function. And you see my disclaimer at the bottom that what we're actually doing, the hard part of what we're doing in this section, is something that is really not calculus at all. Okay? I have had one student that I have known who actually did this in a college algebra course. I was tutoring her, and she was taking college algebra at a school somewhere, and she had an online situation. And I thought, oh my goodness, you're doing this in college algebra. And we did it just fine. I mean, she struggled through it because it's a difficult concept, but it's not a calculus concept. It's just that you don't do anything with it again until Calc 2. So, it says use partial fractions to integrate. Okay. So you'll notice the degree on top is not larger than the degree on bottom, right? This is what I told you. Usually this first step, it's not real frequent that you need it. So we're going to start on step 2. Step 2 says to factor the denominator. All right, so we need to factor 4x squared minus 1. So let's do that. How will that factor? Go ahead. 2x minus 1. Right. This is a difference of squares. 2x minus 1, 2x plus 1. And right now, my students, in fact, all semester, my students in calculus have been complaining about factoring and complaining about trig. They apparently, at least some of them, have had difficulty in those points in their past. And every time we see something with trig in it, or anything we see something with factoring in it, I get complaints. You absolutely have to be able to do both to do calculus. So this is the first step. Everybody okay with the difference of squares on this step? Okay. The second step is to write each of these as a separate fraction. Let me leave it off the top. Don't put anything on the top first. Just write down the two denominators. So 2x minus 1 plus an empty denominator at the moment, or numerator at the moment, and 2x plus 1. What's that? Did I say the wrong thing? Oh, yeah. We're actually separating it so it will be plus. We need to figure out the numerators that will allow this to be true. So our goal is to take something that's multiplication and to separate it into something that's addition. Yeah, you're right, Evan. It looks weird, and it's not true yet. We've got to figure out the numerators that will actually make this a true statement, that I can go from the first line to the second line. What's that? Well, no, unfortunately, it's not so easy to just look at it and say, I think it's going to be. So here's what we do. This is step 2 that we just did, or 3. Step 3 is to write d of x as a summation of fractions. So summation means addition, right? With each factor of d of x as a separate denominator. We've done step 3 now. So we're on to step 4. Step 4 says write each numerator with a degree 1 less than the degree of the denominator. So what is the degree of each of these denominators? 1. What's 1 less than 1? 0. That's the easiest question of the day today, right? 1 less than 1, 0. How do I write a value that has a degree of 0? It would be a constant, right? But we don't necessarily know which constant, agreed? But it is a constant. Well, that's exactly what we're trying to figure out, is we're trying to figure out what those constants should be. So, for the time being, our constants are a and b, and we have to figure out using algebra what a and b are. Okay? So what we do right now is we push pause on the calculus, and we need to do some algebra. And in fact, I'm going to run out of space to make this sort of look reasonable, so I'm going to move this for the moment over here to give myself some space for the algebra. So wherever you're not working on your page, set aside sort of some scratch work on a far left, far right, and call this the algebra step. Okay? Well, we're about to do some algebra. So what does the algebra look like? Well, let me show you. It doesn't look like me moving negative signs. Let me try that again. I wanted this over here like that. All right, the algebra looks like taking a over 2x minus 1 plus b over 2x plus 1. And as counterproductive as what I'm about to do sounds, what we want to do is we want to merge this back into one single fraction. We need a common denominator and merge it back together. No, they're not. Which one's the minus one? My first one? All right, let me get them in there right. Thank you for noticing. The first one is the 2x minus 1. The second one I wrote is 2x plus 1. The order doesn't matter. Just make sure your order stays the same. Mine didn't. It just all turned into pluses. Okay. So the common denominator, of course, is going to be the two denominators multiplied together, right? So the first fraction gets multiplied by 2x plus 1 over 2x plus 1. And the second fraction gets multiplied by 2x minus 1 over 2x minus 1. Of course, the denominator becomes the original denominator I already had from the very beginning of the problem, which is really the goal. The numerator has 2xa, or 2ax, whatever you like. Maybe I'll do 2ax. Maybe that's better. 2ax plus a plus 2bx minus b. I promise this isn't calculus, just algebra. Everybody good with the numerator? What's the numerator supposed to be from the original first part of our problem? It is supposed to be 1. So this thing equals 1. That whole numerator, as ugly as it looks, is really equal to 1. The denominator is equal to 4x squared minus 1, which is our denominator. So our denominators are equal, correct? Which means the numerators have to be equal for this to work as well. Otherwise, the fractions aren't the same. Right? In a fraction, if the denominators are the same, the numerators have to be the same for the fractions to be equal. So what I know is I know that the 2ax plus a plus 2bx minus b equals 1. Okay, the highlighted part that I just created, part of that is variables and part of that is constants, correct? Okay, so which part of it is the variable part? Which terms have variables in it? The 2ax and the 2bx, correct? So this is the left side. We'll call it LHS, left-hand side. What is the variable part on the right-hand side? In the numerator. There isn't one, right? It's 0 x. The left-hand side has a 2ax plus 2bx has to equal 0x from the right-hand side. Let's do the constant part. What are my constants? On the left-hand side, they are a and b, but let's make sure we get our signs with them. It's a minus b, right? And what is the constants on the right-hand side of the numerator? 1. Okay. If you haven't, have you seen this before, Kennedy? Maybe? It looks maybe vaguely familiar, but you're not sure all the details. That's okay. Just curious. Okay. Well, does A equal B? B equal 1? Well, we've got one equation, right? One equation that's got an A and a B and a number in it. But in order to solve equations that have two variables, we have to have two equations, agreed? So what about that other equation? It says 2ax plus 2bx equals 0x. Any thoughts about how we could use that? This piece is actually kind of done. Well, we're going to solve for some things here in a minute.
So could you not solve for a in the constant and then plug it in for a in the variable equation?
You could, but let's clean it up one more step before we do that. Take a look at the left-hand side of the variable equation. What do they have in common? They have a 2x in common, right? In particular, they have the x in common, which is more of my concern. Let's take a look at the, well, yeah, at the x they have in common. If I factor out an x, I've got 2a plus 2b. And on the right-hand side, if I factor out an x, I've got x and I've got 0. That tells you that those parts in those parentheses have to be the same. 2a plus 2b equals 0. Because they are both coefficients on the variable x. So they have to match. 2a plus 2b equals 0. Obviously the 2's are not very important, correct? So really this consolidates even further down to a plus b equals 0. I have the simplest version now of two equations with two variables, which means I can solve them. You've got methods of substitution and methods of elimination. Remember that from algebra? So you could take one of those equations and solve it for a or b and plug it into the other equation. That's called substitution. You could use elimination and simply add these two equations together, which actually works really well on this one, because one of them has a positive b and the other one has a negative b. It's your choice. Do you guys want to use substitution or elimination for this one? Elimination. Thank you so much for being brave enough to give your voice. I like elimination for this one. If I add these together, it's very friendly because I have 2a on the left, I have a 1 on the right, and what is a? 1/2. Using this equation right here, if a is 1/2, what is b? B must be negative 1/2. Because I got to add to 0, right? Why is that valuable? What's that?
Would it have been wrong to, whenever you, the highlighted part, to solve for b, then plug it back in?
To solve for what then?
Like 2ax plus a plus 2bx minus b equals 1.
Uh-huh.
Solve for b and plug that back in.
You won't be able to solve for b because you still would have a and the negative b have to equal 1, and there's two variables with that. Two unknowns. So you wouldn't be able to solve for b directly yet. Here's the beauty though. Your algebra, I don't want to say your algebra's done, but at least the partial fractions algebra's done. Because what we just found out is we just found out that a is 1/2. And b is negative 1/2. So I'll put a negative out here and put the 1/2 here. Is that friendly? It actually is. What's that?
Because A and B are technically constants, and we know that A is equal to B, couldn't we just say that A, they could be any number, make it simpler, we could say they are equal to 1?
Well, but A is not
A
equal to
equals a
B.
negative
A is equal to negative B, and so couldn't we say,
Choose a friendlier number like 1?
no, because that won't actually make the other equation true. They have to have both equations true, right? That, any number would, like, and its opposite would be here, so like 1 and negative 1 would work here, but it wouldn't satisfy the second equation. And that's the problem. Yeah. However, we could do this, and this is what I would do next. I'd think of them as two separate fractions, the 1/2's in front. I've got the 1/over parts inside and so forth. Okay, we are almost done with this problem. I know you're like, is it ever going to end? And to some degree, I agree with you. This is a very lengthy problem, partially because you've never seen partial fractions, most of you, before, or it's been a while. Let's do this piece first. What do I have to do in order to find the antiderivative of this? Okay, what would you like your u to be, Seth?
2x minus 1.
I agree. What would du be? 2, right? 2 dx. And I don't have a 2, so I'm going to have to divide the 2 to the other side. So now I've got a 1/4 integral of 1 over u du. What is that? That's a natural log. 1/4 the natural log of the absolute value of u. Okay, I promise I'm going to come back and get the other half of this problem. But I have 1/4 the natural log of what? 2x minus 1. The other half of the problem is almost identical, isn't it? Yeah, it's going to have the same u substitution, except it's going to be plus instead of minus. So if I did a u substitution, and just so that I don't confuse the issue, I'll call it a v substitution. So this is a v is 2x plus 1. dv is 2x dx, and divide by 2. So when I do my substitution, I have minus 1/4 the integral of 1 over v dv. And what is that? Right, that's negative 1/4 natural log of absolute value of v, which gives me minus 1/4 natural log of 2x plus 1. And there is a plus c. Logs are just so dreadfully easy to simplify that when they are, we should. Yes, exactly. The only reason we can divide them, though, is that we first need to factor out the 1/4. They both have a 1/4 constant in front, right? So if I factor out the 1/4, then I have the subtraction of the two logs. So I have a 1/4. And because the logs are subtracted, I can divide the logs individually, or the interiors of the logs. And this would be the correct simplified version of this particular problem. Do I need the absolute values? I do on this one, right? Sometimes we see them eliminated because we've already got something that we know is positive, but we have no way of knowing whether this value is positive or negative because we don't have a number to plug in, right? Okay, that is your introduction to partial fractions, and we will do one more of those next time and push this off to the completion for this 8.5 until next Tuesday.